Well, in that case, here we are. This is our third lecture on compactness. I had said earlier we were going to do 3 or 4 lectures. Maybe I actually started saying we'd do 2 or 3. Anyway, now we're up to where it's going to be 4. So we're going to do some more compactness today, and then we are going to finish on Friday. The big difference today is that we're going to talk about sequential compactness. Now, that said, first we have a result from last time that we have to go back and prove because we didn't do it last time. So I'm going to start with the result. It's out of the lecture notes that I posted for the last lecture, except we just didn't mention it in lecture. So in those lecture notes, it's proposition 2.2.3. So this is in the lecture 8 notes. And by the way, when we're done with all the compactness, I will post just all the notes for compactness all put together, so you don't have to remember which lecture they're in. And here's the results. In every metric space, all compact sets are closed and bounded. Okay. So last time we proved at the end of lecture that if you're in the reals and you are closed and bounded, then you're compact. This result says no matter where you are, compactness means closed and bounded. So once we've got this, we'll be able to say that in the reals, compactness is the same as closed and bounded. Okay.
Dr. Goddard?
Yeah.
I understand what bounded means on the real line, but what does bounded mean in a general metric space?
That is our first task, is let's define what bounded means. Okay. So we will define that. So we've got a subset, and we want to say what it means to be bounded in a general metric space. Okay. On the reals, bounded means contained in an interval, right? Now, when we go from the reals to an arbitrary metric space, our intervals kind of turn into balls. And so now what we're going to use is instead of contained in an interval, we'll just use contained in a ball. So what does that mean? Well, that means that there's some point and some radius so that S is contained in that ball. And that's what I'm going to write. Okay. So, before we start the proof of the proposition, are there any more questions? No? Okay. So we're going to take an arbitrary compact space, and we've got to prove that it's closed and bounded. So we know where our proof's going to start. Let K be a compact set in the metric space XD. Okay? Now, we'll do bounded first, because bounded is a little bit easier than closed. For bounded, the way we're going to cover our set is we're going to take any point in the space and we're going to take increasing balls around it. So let's fix some x naught in the space. And here's the point. Our compact set K, well, obviously it's contained in the set X, because X is the space. But then we can write X as the union from n equals 1 to infinity of the ball centered at x naught of radius n. Why is that? Well, I mean, you take any point in X, it's at some distance away from x naught. And so it's going to end up in, actually in all of these balls, as long as n is sufficiently large. Okay, so our picture here would be that we've got an x naught, and now we're forming concentric circles. Okay. Now each of these is open. So this is an open cover of K. It's the set of these sets, the family of these sets, is an open cover of K. Now, what does compactness tell us here?
You can select like finitely many balls, and that will also cover the set K.
Mm-hmm. By the compactness of K, we have a finite subcover, but now let's go one step further. What's a finite subcover here? Yeah. There's a finite number of balls that together cover K, but the balls are concentric. So one of those is the largest. So there is some capital N I guess it's a natural number such that K is contained in the ball centered at x naught of radius capital N. And that's the definition of bounded.
So the reason we need compactness is because we need to be able to invoke the there's a maximum of a finite set, or there's a maximum natural number. Well, yeah, there's a natural number on a finite set of natural numbers, there's a greatest element.
Well, compactness lets us get there, yeah.
Right, okay. Because it seems like from without the compactness, it seems like then everything would be bounded, but we need the compactness to be able to say there is some biggest circle.
Mm-hmm.
Okay.
Yeah, I mean, just think about the real line. The entire real line is not a compact set. Okay, because it's not bounded. And if you form these concentric circles, you get more and more and more every time. Okay? But that doesn't happen with a compact set. Because with a compact set, when you form these concentric circles, at some point you have to stop getting new stuff because you have a finite subcover. Does that make sense?
Yeah, it makes sense. We have to be able to chop off the infinity to make it work.
Right, and that's that's exactly how we use compactness all the time. So this is why it shows up all the time. All right. Let me draw your attention to one other thing in this proof. In the definition of bounded, we said if there's some point x that we can center this at. Well, in our proof, we actually just let x naught be arbitrary. It doesn't matter what x naught is. So what's going on there?
I guess there's some freedom in the boundedness.
Mm-hmm.
I don't know what that necessarily means. I guess it's just convenient for us.
So what's going on here is that if you're bounded with one choice of the center x, you're actually bounded with any choice of the center x. Okay? Because with any other choice of the center, you can just increase the radius, and then you'll see that you're going to be bounded with respect to that other center by the triangle inequality. Okay. So if you're if here's x naught. Here is your concentric circle that your set is in. Your set is these things in there. Here's the other center you want to use. Let's call it x1. Well, just pick a larger circle that encloses the old circle, and then you're good. So, in the definition of bounded, it doesn't matter what your center is. The bounded sets don't change. Okay, before we go on to the second half of the proof, one more thing you should think about. What are the bounded subsets of a discrete metric space?
Well, it would be all of them, correct? Because all the points not equal to your point are just going to be distance one away.
Mm-hmm. Yep. So they're all in a ball of, I don't know, radius 2. Mm-hmm. A ball centered anywhere of radius 2. Yep. Okay, now, why are compact sets closed? Okay, now, it's going to be a recurring theme throughout the course and throughout your mathematical lives, as long as you're studying things that involve point set topology. You almost never prove that something's closed. You prove that the complement is open. So we want to prove that the complement is open. Now to prove the complement is open, you take a point in the complement and you find a neighborhood that's in the complement. So we're going to do that. Okay, so that's bounded. So now, okay. One special case, if no, I'm sorry, we don't need to make this special case. Never mind that, erase that. Let's choose a point, y, in the complements. That's that wrong complement. In the complement. And we're going to let this be an arbitrary point. Now we're going to do the same thing. We're going to take an open cover. We're going to have a finite subcover that's going to give us a neighborhood. Okay. Except now our open cover is not going to be concentric circles at y. It's actually going to be their complements. Okay. So for each integer n at least one define, these are the sets we care about. The set of points that are a distance greater than 1 over n. So our first one is the outside of this circle of radius 1 centered at y. Our second one would be the outside of the circle of radius 1/2 centered at 1, and so on and so forth. Okay. What do we get when we take the union of all of the v sub n?
Is that the whole space X?
It's not the whole space.
Punctured disk.
Punctured space, yeah? So when we union those guys up, the only point we're not going to get is y. So everybody see that? Every other point is some distance away from y. And that distance it is away from y will be greater than 1 over n for some integer n. Okay. So I guess if you insist, we're using Archimedean properties here. I'm sorry. Can you hear me over the lawn mowing that's happening?
Yeah, I can hear you.
Okay. I can sort of hear you. Sorry about that. That's unfortunate timing. Okay. So we've covered everything except for y. But y was in the complement. So this means we've covered k. So the set Vn is an open cover of k. So it has a finite subcover. And now again, we're going to, just like we did in the other half of this argument, we're going to skip ahead to say, well, there's some largest n so that blah, blah, blah. So there is, I'll just copy the line from the other half of the proof, essentially. There is some n such that, oops, I want to have there be a capital N down there. Such as the entire compact set K is contained in V sub capital N. And I'll just repeat the definition. What was that? That's the set of points that are at distance greater than 1 over capital N away from Y. Now, the importance of that is that now we have found that there's an entire ball centered at Y that's in the complement. And why is it in the complement? Well, it's not in the set. So, hence, well, I'll just skip to that. The ball centered at Y of radius 1 over capital N is contained in the complement of K. So the complement of K is open. So K itself is closed. Okay, any questions?
Can you go over the the line that's K is a subset of Vn, hence the ball is in the complement? Could you maybe point that out on the picture?
So this, and then hence that, right there?
Yes.
Right. So we're getting concentric circles. Except now our sets are their complements, so our sets are the stuff outside, right? And these concentric circles are narrowing in on Y. But at some point, we stop and we say, we've seen our entire set K. So what does our set K look like? Set K might look like that. Okay? And in this case, what we would do is we would say, well, this circle, once we've got the complement of that circle, that contains K. And then what we say is, so the neighborhood, the neighborhood of, well, that is a neighborhood of Y, or its complement is a neighborhood of Y. So we've got a neighborhood in the complement.
My main worry with that is I'm just a little confused because we're using 1 over n, and I just am unsure of like the boundaries, like the distance 1 over n. To me, it looks like they overlap. Could you maybe
Sure,
show
sure.
that they don't? Because to me, it looks like the ball, the edge 1 over n is in both. Well, I guess it's in none of them.
Yeah. I mean, they're all open sets. They don't contain the things at distance
Okay.
1 over n. And yeah, I mean, these overlap. Yeah, they're nested. They get bigger and bigger and bigger.
So I guess the circle where everything is 1 over n away from the point y, that isn't in either of these sets, the ball or the
Right.
vn.
Yeah. Right.
Okay, that makes sense. Okay.
And I guess what I was saying was, well, it's in the next ball. Oh, sorry, it's in the next complement or whatever. It's in the next VN. Okay. Let's see. I got a question from Benjamin in the chat. If guess what we can establish, let's say we define. Yeah. Yeah. So what have we proved? We have proved. In an arbitrary metric space, so XD will always be an arbitrary metric space, compact implies closed and bounded. We've proved in the real numbers with the standard metric, closed and bounded implies compact. Okay.
Dr. Bader,
Yeah.
are you writing right now? Because the screen hasn't changed for me and the timer on the... Okay, there we go.
Oh, weird. Okay.
Okay.
Sorry. I know what I did. Okay. Hopefully I won't do that again. Okay, so in an arbitrary metric space, compact means closed and bounded. Sorry, it implies closed and bounded. In the real numbers, closed and bounded implies compact. So in the real numbers with the standard metric, compact is just the same as closed and bounded.
Dr. Vater, but haven't we proved only that closed and bounded intervals in R imply compact?
No, so last lecture we started with that. And then we proved if you're a closed subset of a compact set, then you're compact.
Oh, I see. Oh, okay. So you can just like have an interval that covers like everything, like the whole set, and then like that will be closed and bound. Okay, thank you.
Mm-hmm. Yeah. So we first, for this result here about the real numbers, we first proved it for intervals, but then we proved another result, and then we got as a corollary this much stronger result that closed and bounded implies compact. Okay, so for the real numbers, compact is exactly the same as the conjunction closed and bounded. Can anyone think of a metric space where that is not true? The rationals. Now that's interesting. So let's see what I'm asking for. I'm asking for a metric space where this is not true. So the question is there a metric space where there is a closed and bounded set that is not compact? So Madeline has the right answer. Not the right answer. She has a correct answer. But I'm sort of interested in this question about what about the rationals? Any thoughts on that? Could you have a closed and bounded set in the rationals that's not compact? And then we'll go to Madeline's answer. But first, let's answer this one.
So for the rationals, since compactness doesn't care about the ambient space, we can think of the rationals being embedded in the reals, and then any closed set of rationals is going to be a subset of a closed set of reals, a closed and bounded set. So so the compactness will follow from there.
Mm-hmm. So remember, I believe this was the first lecture on compactness. We proved that compactness is an intrinsic property, which means it doesn't depend on the ambient space. So the set K in the rationals is compact in the rationals with the metric if and only if K is compact in the reals. Okay. Now, it doesn't it doesn't quite answer our question, right? Why doesn't it answer our question?
Well, don't we need to also mention that if K is closed and bounded in the rationals, it's also closed and bounded in the reals, right? And then isn't that enough to?
Mm-hmm. So bounded in the rationals is clearly the same as bounded in the reals. What about closed?
Oh.
Because that's the thing. Open and closed are not intrinsic properties. They can change based on the ambient space. So Benjamin, you pointed out, you have an example. You said pick any irrational number as your supremum. Mm-hmm. Mm-hmm. That's an issue. So, let me simplify Benjamin's. Construction. Let's just do 0. Consider that interval in the rationals with the standard metric. Now, since it's got that irrational endpoint, this interval is the same thing as this half-open interval. But the question is that closed? Madeline says it's not closed. Why isn't it closed, Madeline? Ah. Madeline says I can take a sequence of successive approximations to pi, and my set won't contain the limit, so it's not closed. You're assuming my space is complete, and it's not. My space doesn't have a limit. So that sequence doesn't have a limit in Q. And since it doesn't have a limit, my set doesn't have to contain the limit. Does that make sense? So that's the point. That sequence, your sequence of successive approximations to pi, does not have a limit in this space we're talking about. And so we don't have to contain it. So the easiest argument here is to say, think back to our lecture on relative topology. You're going to be closed in the rationals if and only if you're a closed subset of the reals intersected with the rationals. Now, what are we? We are a closed subset of the reals intersected with the rationals. So we're closed in the rationals. Now, why does that make any sense? Yes. So if that relative topology argument is not thoroughly convincing to you, and I don't think it's thoroughly convincing to me, what I would rather see is a proof that its complement is open. Okay? So here's our claim. This quote-unquote half-open interval is closed in QD. So equivalently, its complement would be open. Now, what's its complement? Its complement is minus infinity to 0 union pi to infinity is open. Okay? Well, you got a union of two sets. If they're both open, then their union is open, right? I hope everyone's going to agree. And sorry, I should add the in the rationals. Okay. Now, I hope everyone will agree that this set from minus infinity to 0 is going to be open even in the rationals. Every point in there is going to have a neighborhood in there. Okay. What about the other set? Why is the closed interval from pi to infinity open in the rationals?
that's just equivalent to open pi to infinity, right? Which is just an open interval.
Mm-hmm. It's exactly the same as the open interval from pi to infinity. Okay, one more thing. What was the point I was going to make? Oh yeah, I just wanted to point out. Okay, if you were going to say this half open interval from 0 to pi is not closed in the reals, because we know it's not closed in the reals, what would your argument be? Well, your argument would be, look at pi. Pi is in the complement, but it doesn't have a neighborhood in the complement because any neighborhood of it will contain numbers less than it that are in the set. Okay? But you can't make that argument when we're in the rationals because there's no pi. So you can't say look at pi because there's no pi. Okay? You would have to say look at a number, just a little bit bigger than pi. But then that little bit bigger than pi is going to allow you to fit a neighborhood into the complement. Okay? So now, what have we done? What have we done? We went on quite a little tangent there. We have a closed and bounded set. What have we done? We have shown that 0 to pi is closed and bounded. In QD. Is it compact there? And Daniel, now would be a good time to repeat what you said earlier.
Yes, it is because because this. What?
No, it's not.
It's not? Why not? I thought we were a subset in the ambient space and whatever.
Oh, okay. Yes, compactness is intrinsic.
Mm-hmm.
This set is not compact in R because it's not closed and bounded in R.
I see now.
Mm-hmm. So this set is not compact in QD. Okay? And the reason, the quick reason that it's not compact in the rationals is that it's not compact in the reals, and compactness is intrinsic. So, so what happened here? We said when we're switching between the reals and the rationals, boundedness doesn't change. A set is bounded in the reals if and only if it's bounded in the rationals. Compactness doesn't change because we've already proved a lecture or two ago that compactness is intrinsic. So that can't change when we pass between when we switch between the rationals and the reals. But closedness can change. So open and closed depends on the ambient space. So we had a set that wasn't closed in the reals become closed in the rationals. But it didn't become compact. So again, what we've shown is we found a metric space where compactness is not the same as closed and bounded. Okay. Now it is still true. This line, what we proved at the beginning of today's lecture. One, two, all. Okay. What we proved at the beginning of today's lecture is still true. Any compact set in the rationals is going to be closed and bounded in the rationals, as this one is. But this converse that was true for the reals is not true for the rationals. Okay? Now, what was this all in answer to? I had asked, can you think of a metric space? This question. Can you think of a metric space where there's a closed and bounded set that is not compact? And we have just come up with a metric space and a closed and bounded set that is not compact. And I said at the time, Madeline came up with the easy answer, which is the answer I was thinking of, which is also any infinite space with the discrete metric. Okay. Then you look at the space itself. The space itself is going to be closed because the space itself is always closed, and because when we're in the discrete metric, every set is closed because every set is open. It's bounded because we talked about that at the beginning of today's lecture. Every set in the discrete metric is bounded, but it's not compact because we've talked about this before. Compactness in a discrete metric space is the same as finiteness. And we've assumed that this space is infinite. Okay. I hope that was helpful to go into those examples and kind of illustrate this. That wasn't planned, but I thought that worked out really well, and that actually saved us from like getting halfway into sequential compactness and having to stop. So the plan is next lecture we will do, well, we'll see. We'll do sequential compactness and we'll see how far we make it. Okay. So that's the end of today's lecture, and I will stick around if there are any more questions.